Okay. I think we can start.
Yes.
Okay, so hi everyone. Welcome to this online appointment with the non-associative algebra seminars. It's my pleasure to introduce today's speaker, Anastasia Doikou from the Heriot-Watt University of Edinburgh. She will speak about parametric, set-theoretic Yang-Baxter equation, p-shelve solutions, and quantum algebras.
Okay, thank you. Can you see my whole screen?
Yes.
All right. Because I'm having a problem, I cannot see my own screen very much. So give me just a moment to see how it goes here. Okay, good. I think now it's better.
Yes.
So thank you very much for your kind invitation. Thanks, Paula. So indeed, I'm going to talk today for some new work on the parametric set-theoretic Yang-Baxter equation. And I'm going to talk about some new objects, which I call p-shelves, and solutions and quantum algebras. So to start with, I will give some, again, I made something wrong, sorry. All right. So I will start with some general motivation and some general history of the object. What is Yang-Baxter equation? Yang-Baxter equation first appear in the context of quantum integrable systems, which are statistical models of one dimension. Sorry about that. Of one dimension. And these objects are central in order to prove the integrability of the system. And physically, Yang-Baxter equation and the solution, the R-matrices, physically describe interaction between particle-like excitations displayed by these systems. And the Yang-Baxter equation is basically the factorization of these interactions. But also this object, Yang-Baxter equation, is a central object in the definition and derivation in Hopf algebras, independent quasi-triangular Hopf algebras in particular, independently introduced by Drinfeld and Jimbo. And this is one of the main objects of what we call algebraic quantization in integrable systems. Of course, there are various connections in other mathematical objects, in particular braid theory, Hopf algebras in general, knot theory, low-dimensional topology, Hopf-Loa extensions, more recently hips and trusses, which are ternary objects, and so on. Here I'm going to consider a particular notion of a set-theoretic Yang-Baxter equation, which was introduced by Drinfeld sometime in early 90s, in 92 in particular, and then studied for the first time systematically by Entikov, Settler, and Soloviev. In this case, solutions were found, and a general discussion about the underlying quantum groups were discussing. But in this case, all the discussion was about the non-parametric Yang-Baxter equation, and not the parametric one, which is the one I'm going to, the one I'm going to consider here. So there are very interesting connections with subjects that call geometric crystals and cellular automatons. And from the classical discrete integrable systems point of view, solutions of this equation, the set-theoretic Yang-Baxter equation, are known as Yang-Baxter maps, which are discrete maps and describe soliton interactions. And in this case, the set-theoretic Yang-Baxter equation turns out to be parametric. Recently, the last 15 years or so, there's a whole bunch of people working on solutions of the non-parametric Yang-Baxter equation, and the notion of braces, which I will explain later what it is, were introduced by Ram first and then extended by Guarnieri and Vendramin under the name of skew braces. So here, as I already said, for the first time, I'm going to follow an algebraic approach for the parametric case, where so far only the non-parametric case were studied from the algebraic point of view. And I will discuss the algebraic approach for the parametric case, although the basic blueprint, at least for the study of the underlying Hopf-like algebras, were introduced by Bernard Rybolowicz, Paola Stefanelli, and myself in a previous paper. The talk is basically divided in two parts. In the first part, I'm going to introduce the notions of the parametric shelve and rack. These objects are generalizations of the usual shelves and rack, and they satisfy some parametric type self-distributivity condition, and they naturally lead to solutions of the Yang-Baxter equation. Then I'm going to derive a so-called admissible dreamfield twist, which will allow me to derive more general set-theoretic solutions. And some prototypical solutions are going to be presented also here. Then in the second part of my talk, I'm going to formulate the underlying quasi-triangular Hopf-like structures. These are certain examples of special quantum algebras. In fact, this is a new paradigm of quantum algebra, as opposed to the most well-known examples coming from quantum integral models, such as the Yangian or the Q-deformed algebras. So I'm going to start with some definitions. So I'm going to start with two sets, non-empty sets, y, x, and y. Y in general is a subset of x. And there are some parameters, z, I, j, that are elements of y. Ij takes values from the positive integer set. And then I define a map from x cross x to x cross x, such that for all elements x and y in x, the map Ryx goes to sigma xy tau yx with parameters zij. Whenever I write zij, simply this shorthand notation denotes dependence on zi, zj. So the order of the parameters, of course, is important and plays a role. And we say that this map is a solution of the parametric set-theoretic Yang-Baxter equation if this relation is satisfied. So each one of the matrices has a pair of parameters zeta 1, 2, 1, 3, 2, 3, and so on. And of course, the indices, the sub-indices 1, 2 means that R acts on the first two elements of the triplet, 1, 3 on the first and the third, and so on. Some extra definitions, we say that R is a left non-degenerate solution if for all the parameters Zij and all x in set x sigma Zijx is a bijection, and in general non-degenerate if both sigma and tau are bijections. So these are some introductory definitions to set up the scene. And also some extra definition coming from people basically that work on discrete integrable systems. A solution R is called reversible if this relation here is satisfied. And whenever I say R21, I mean the composition of R with the flip map. So we swap the two positions in the pair AB. So the flip map takes AB and sends it to BA. And just a useful information here, all available solutions we have so far for the parametric Yang-Baxter equation are all reversible, namely they satisfy this condition. So here we show that reversible R-matrices, all reversible R-matrices, parametric R-matrices are reduced to the identity map. And also for the first time, we're able to derive algebraically some new solutions that are non-reversible. So we start with my first definition. I start with the two sets again, and with the parameter Zij on Y, and I define a parametric binary operation, let me call it triangle Zij, that takes you from x cross x to x and sends every pair AB to a triangle B. So we say that the pair X triangle is a left parametric p-shelve. P is for parametric. If the triangle operation satisfies the generalized left p-distributivity condition, which is like that. So in the usual case of shelves, you don't have the parameters. Okay, it's a simple self-distributivity condition. All right, and this is true for all of the elements A, B, C, Z, I, J, K. And moreover, a left p-shelve is called a p-rack if the triangle map, like that, is a bijection. A triangles Aij is bijection. And so from now on, whenever I say p-shelve or p-rack, I simply mean left p-shelve or left p-rack. So just saving some words. Okay, now one of the main propositions, the first proposition comes. If I have a set X and a set Y, Y is subset of X, and the operation triangle, like that, then the map R, such that is defined in this way, that is RBA is B triangle A, is a solution of the parametric set-theoretic Yang-Baxter equation if and only if X triangle is a p-shelve. The proof is quite straightforward. So if you start with a solution of the Yang-Baxter equation, then you plug in this form of the matrix in the Yang-Baxter equation, and you equate the left-hand side with the right-hand side, and this is precisely what you get, which is a generalized parametric self-distributivity condition, which is precisely the definition of a p-rack, of a p-shelve, sorry. And vice versa, if X triangle is a p-shelve, then automatically this map here, R, this map here, is a solution of the Yang-Baxter equation. And in addition, if your solution, if X triangle is a p-rack, then you end up with an invertible solution. And that's obvious because now your triangle operation is a bijection, so you can define the inverse of it, and thus you can define the inverse R matrix. This is quite a straightforward statement. So first thing, by just introducing that generalized concept of p-racks, we were able to find solutions of the parametric set-theoretic Yang-Baxter equation. And let me now show you some specific example based on the construction of braces. Let me remind you what the left skew brace is. Again, I remind you that the notion of brace and skew brace particularly was invented in the context of the set-theoretic Yang-Baxter equation to provide solutions of the equation. So what is a left skew brace? Is a set B together with two group operation, plus and circle. And the first is called addition and the second one is called multiplication, such that for all elements in B, this distributivity condition holds. Okay, you have the strange A in the middle, so it's not the usual distribution condition. Its distribution condition is a bit more complicated. It's related also with the notion of trusses. We've heard some talks previously by Robert and by Bernard and Thomas a week ago, actually. So if in particular plus is an abelian group, then B is called a left brace. And similarly, if you have a right distributivity, then you have a two-sided skew brace and brace analogously. The interesting observation here is the additive identity of a skew brace, if we denote it by 0, and if we denote by multiplication, it turns out that for every skew brace, 0 is 1. Again, from now on, whenever we say skew brace, we simply mean left skew brace. So the left distributivity holds. Okay, specific solutions now. So consider that you have a skew brace, and then psi is a subset of X. And then all elements z of y should satisfy the right distributivity as well in that sense. And also z are central elements in X plus. So you have these two extra conditions for z. And define also for all the parameters zij in y this binary operator, triangle, such that a triangle B is defined like that. Okay, so it's quite symmetric. Is minus a zij plus b plus a multiplied by zaj minus 1. Minus 1 is the inverse with respect to the circle operation, of course. And in the parameter-free case, of course, you have something which is familiar, is a typical shelf action. Then this map, expressed like this, is indeed a solution of the parametric Yang-Baxter equation. Again, the proof is a straightforward computation. You just plug in the solution in the Yang-Baxter equation, and it turns out that the triangle satisfies the self-distributivity condition with the parameters, which means that X triangle is a rack. So R is a solution of the Yang-Baxter equation. And not only that, it turns out that A triangle is a bijection, and the inverse action is given by this expression here. Again, it's quite symmetric. The first, the minus become plus, and the plus becomes minus in your expression here. So this is a concrete example of solution based on the existence of brace. And how about more general solutions, right? Before I talk about more general solutions of the set-theoretic Yang-Baxter equation, let me just make a remark. In the special case when we're talking about a brace, namely X plus is a billion, then the triangle operation just reduces to B. It's trivial. It's a kind of degenerate. AB is B, and hence the R-matrix is the identity, is a trivial solution of the Yang-Baxter equation, okay? But now, as I said, I'm going to consider the more general class of solutions of the set-theoretic Yang-Baxter equation. And now R is a map from X cross X to X cross X again, that it has this form for any AB and ZAJ in Y. So it takes a pair BA and it maps it to sigma AB tau BA. So that's the most general solution. And I'm going to describe how can we get such solutions from the P-rack solutions. So the first thing we need to do is to find out what are the necessary and sufficient conditions of having a solution of the Yang-Baxter equation. So if you consider this map of this form, where sigma and tau are just functions from X to X, like this, and the map R has this general form, then R is a solution of the parametric set-theoretic Yang-Baxter equation if and only if, for all the parameters Z1, 2, 3, elements of Y, these three quite complicated conditions are satisfied. For people that are familiar with solutions of the set-theoretic Yang-Baxter equation, we will immediately see some conditions, familiar conditions, if you forget the parameters Z1, 2, 3. So these are the typical parameter-free conditions of the Yang-Baxter equation. Of course, now the problem due to the complex dependence on the parameter becomes a bit more complicated. Nevertheless, is still tractable precisely in the same way that is for the non-parametric case. And so in order to proceed, let me just first define the notion of a Drinfeld twist. And after that, I'm going to define the notion of an admissible Drinfeld twist. So let me consider two solutions, R and S, of the parametric set-theoretic Yang-Baxter equation. Then we say that the map that depends on the parameters Zi and Zj from X cross X to X cross X is a Drinfeld twist if for all the parameters this relation is satisfied. right? Is an entwining, intertwining relation essentially, where phi op, it simply means the composition of the flip map with phi, okay? I remind you, pi is the flip map such that for all x and y in X, phi xy is yx. If in addition, the map phi is a bijection, we say that the solutions R and S are d-equivalent, Dirichlet equivalent via the map phi, and we denote it like that. So this is a very natural extension of what's going on in the non-parametric case, discussed in the paper with Bernard and Paula. And now the proposition comes, if you have R be a left non-degenerate solution. Remember, a left non-degenerate solution means that sigma is a bijection. So this is the map R, and sigma is a bijection. And also S is a solution such that is of this form, is a p rack solution. But now we identify tau in this form, okay? This is the inverse of sigma with parameters, and also depends on the action of triangle, of the p-rack action. It turns out that if I define things in this way, then R and S are d-equivalent. Well, the proof is, again, straightforward, as long as I'm able to identify the suitable phi. Indeed, if I find a phi, a map phi, which is defined like this, now it depends only on sigma, on the bijection, so automatically phi is invertible. And then R is a left non-degenerate solution because sigma is bijection. And if I define what is the inverse, phi minus is defined like this, a sigma minus, and the opposite phi is defined like this. So I have all the ingredients I need. So if I now concretely compute this object, is almost a similarity, but not a similarity transformation, in the sense that now I have this operation here. And if I do that, I end up that after I multiply from the left and from the right, I act from the left and from the right with the map phi and phi op, I end up to R. So indeed, the two solutions are d-equivalent, right? As long as tau is identified in this way. So it takes some computation to show that, but nevertheless, it's a straightforward computation. Again, in the special case of a reversible R matrix, namely, if this condition is satisfied, you can immediately show that this condition is satisfied. And if you look the identification of tau, you will immediately see that this BA becomes A, and automatically S becomes the identity matrix. So for all reversible solutions can be somehow are d-equivalent with the identity map via this concrete phi matrix. But this observation, this connection between p-rack solutions and general set-theoretic solutions can be further explored, and it can be generalized to a more general statement as a theorem. But before I go on and formulate the theorem, let me start with the definition of an admissible twist. So if I have a p-shelve X, a triangle p-shelve, and we say that the twist phi, such that it maps AB to A sigma AB, is admissible if these two conditions are satisfied for all A, B, C, and Z, I, J, K. So if you notice, the first of the conditions is just, if I go back a couple of pages, this is the first of the conditions that comes from the solution of the Yang-Baxter equation, is the first necessary condition if I have a solution of the Yang-Baxter equation. The second one If you forget a bit about the parameters, in the free parametric case, you see the sigma is basically a rank homomorphism, as you can clearly see from the form. Here is a bit more complicated, but nevertheless, you have these two concrete conditions that sigma and the triangle, the rank operation, need to satisfy. Okay, and now we can come to the main theorem. If you have a p-shelve and you have the map phi defined as usual in this way, AB goes to sigma AB, then the following map R defined in this way. You have again AB goes, sorry, this is wrong here. I meant to have BA. This is a typo. So the pair BA maps to sigma AB and tau BA, where this is the tau identified like that. So this R is a solution of the Yang-Baxter equation if and only if phi is an admissible twist, namely phi satisfies these two fundamental conditions. The proof for the parametric case is awfully involved. Nevertheless, it goes through. And basically what this theorem tells me is that every set-theoretic solution of this general form can be obtained from a p-shelve solution, where I identify the p-shelve like that, by an admissible twist. So if you have a twist and a p-rank solution, you automatically get a solution of general set-theoretic solution of the Yang-Baxter equation, and vice versa. If you have a solution of the Yang-Baxter equation, you can identify a p-rank from it via an admissible Drinfeld twist. And of course, if you have a left non-degenerate solution, is bijective if and only if your self is a rank, which is a very immediate consequences of the discussion we had previously. So basically, the problem of identifying and classifying, if you wish, all the general solutions of the set-theoretic Yang-Baxter equation is now reduced to the classification of the p-shelve rank solutions. So basically, a classification of parametric shelves and ranks is in order, study of representations of sub-objects, and so on. And again, in the reversible case, it turns out that you have a bijective map, and the only thing you need is this condition. And of course, the fact that this condition here is going to give you B. It's going to be trivial. So pretty much this concludes the first part of my talk, which has to do with solutions, general solutions of the set-theoretic Yang-Baxter equation coming from p-ranks, parametric ranks, and the admissible parametric twist. But let me now give you a concrete example of solutions coming again from braces. Again, I have a skew brace, and I had exactly the conditions I had before, namely Z satisfies a right distributivity condition, and Z elements of Y are central not only in plus, but in circle, and the circle operation as well. And we define the admissible twist like that, where sigma is given by this expression here. It's a very concrete expression in terms of the two skew brace operations. And we also define a triangle as we defined it before in the same way. So if you have these two concrete expressions for sigma and a triangle, then you can show that A circle B satisfies sigma A Zij tau B Zij A is the analog of what people know as a structure group. And also phi is an admissible twist. Okay? So the first part, in order to show the first part, you need to identify tau, but you can do that because you can identify sigma minus 1. And you can also identify then tau because you have sigma minus 1 and you have what a triangle is. And if you do that, and you go ahead to compute using the properties of braces, you indeed show that this condition is true. In order to show that phi is admissible, again, using the explicit expressions for sigma and a triangle, you can show the two conditions of admissibility that I showed in the definition of an admissible twist. It's quite lengthy, not very lengthy, but it's a straightforward, again, computation. So again, in the case, of course, of when we're talking about a reversible solution, X plus is abelian, S becomes the identity map because A triangle B becomes B, and the R matrix again is of the general form, but now is reversible, namely it satisfies this concrete condition here of reversibility. And in accordance to the main theorem, all reversible solutions can be obtained from the identity map via an admissible twist. So this pretty much wraps up the discussion about solutions of both Pirac and general set-theoretic solutions. And as I said, now I'm going to continue the discussion about the linearized version. I'm going to use the linearized version of the Yang-Baxter equation for the study of the underlying quantum algebra. So for simplicity here, I'm going to consider a finite case, although this can be generalized for infinite and compact sets, but let me consider some countable finite sets for simplicity. So I'm going to consider a free vector space, or a linearization of X, and of a dimension equal to the cardinality of X, and the basis B, where this element EA can be thought of as n column vectors with 1 in the position A and 0 elsewhere. And of course, you have the dual basis, and A star B is delta AB, is an orthonormal basis, and AAB is a matrix with 1 in the position AB and 0 elsewhere. And of course, now R is an n square by n square matrix with parameters ZA, and it satisfies the so-called quantum parametric Yang-Baxter equation sometimes, or the tensor Yang-Baxter equation in this form. And now the notation changes a bit. The indices 1, 2 simply mean the action of R in the first two copies of the vector of the tensor product. R1, 3, it's an action on the first and the third, and so on. So this is the setting I'm going to consider from now on, the tensorial language. And of course, for set-theoretic solutions, in the set-theoretic case, these are, of course, objects that call Boltzmann weights and have to do with a configuration of probabilities of configurations in two-dimensional lattices. For people that use solutions of the Yang-Baxter equation to construct two-dimensional physical lattices. But anyway, I'm not going to say much about it. I will just say that in the set-theoretic case, you have some delta distribution. It's a product of two delta functions. In this way, similarly for the p-shelve Pirac solutions. And so in the remaining of the time, I will try to establish the general algebraic framework in the tensor product formulation, and also explore the quantum algebras, the coproduct structure associated to these algebras, and also derive the so-called universal R matrix associated to both Pirac and general set-theoretic solutions. All right. So I'm going to start with the definition of the so-called Pirac algebra. The name is a bit strange, but it will be fully justified in a bit. So for the moment, again, I have the two sets, and Y is a subset of X. All the parameters Z are elements of Y. Again, I have the usual binary operator triangle. And in general, this X triangle is a finite magma or such that A triangle is surjective. So we say that the unital associative algebra Q over some field K generated by 1, which is the unit element, Q minus 1, which is the inverse, and HA such that H, or for all H, you have this equivalence here. And these relations, the first one is a trivial invertibility condition. This is the main algebraic relation between QAs and QBs, and this one. So you have relations now among families of generators, parametric families. So if all are satisfied, this is a Pirac algebra. Okay, so it's a concrete quadratic algebra for generators. Then the choice of the name will be justified now with the following proposition. So if you start with the Pirac algebra, then you can immediately show that the self-distributivity condition, parametric self-distributivity condition holds. All you need to do is to use the associativity of the algebra and compute this object in two distinct ways according to the associativity. If you do that and you use the algebraic relations of the Pirac algebra, you end up to this condition. Remember, these objects are invertible, so you can get rid of them by inversion. And this leads immediately to this self-distributivity condition. Okay? Now, if in addition, you can show that A is always a bijection, so in every case, X triangle is a Pirac, and hence the name Pirac algebra. Two useful observations. If you take the sum of all generators HA, then it turns out that this is a central element of the Pirac algebra, and you can immediately then show that H square is HA, which means that HA are R projectors. And also, if you take the sum over this the family of QA generators, in fixing the parameters IK, you can show that this object TIK provides a family of commuting objects in the sense that for two distinct IJ, this TJK, TIK commute with each other. This is a primitive statement of quantum integrability. I'm not going to say much about that, but coproducts and coproducts of these objects here, the commutation of coproducts of these objects, indeed provide the definition of quantum integrability in this setting. Okay, and now once we have introduced the universal algebra, Pirac algebra, we can identify the universal R-matrix associated to this algebra. So again, I'm sticking to the Pirac algebra, and I have a general element of the Q tensor Q with parameters Zij, elements of Y. And this is an invertible element, and in fact, I choose to write it in this form as a sum over A are elements of X, HA tensor QA Zij. You see the parametric dependence here on Q. Then these R is a solution, satisfies the parametric Yang-Baxter equation. You can show that is a solution of this generalized universal Yang-Baxter equation, where, again, the notation is the usual notation. And also, you can show that there's the inverse R matrix, which has this form. The second statement is quite obvious. So all you need to do now is substitute the expression of R in your universal R matrix, use the algebraic relation, exploit the fact that A triangle is a bijection, and then the left-hand side is equal to right-hand side. So indeed, this is true, which means that R, the scarcely R satisfies the Yang-Baxter equation. And because of the fact that sigma HA is 1, we proved at the beginning that this is a central element, and you can choose this C to be 1. You can also identify the inverse matrix. So by identifying the P-rack algebra, we were able also to find the solution of the universal R-matrix solution of the Yang-Baxter equation. So how this universal solution is identified with the solution I found at the beginning, the P-rack solution. Well, let me recall again, this EIJ is an n by n matrix with entries 1 at the position ij, the entry ij, and 0 everywhere else. And let Q be the rack algebra, and you consider a representation from the algebra to the homomorphisms of V. And so every element of the algebra is mapped to an n by n matrix in that way here. And then the R matrix is mapped to this n squared by m squared matrix, but this is nothing but the linearized version of the P-rack solution in accordance to the linearization process I described before I start discussing about the algebra. But of course, this is too general, and because we would like to have some notion of co-associativity, associativity, and co-associativity, I'm going to introduce an extra algebra and an extra structure, algebraic structure. So I call a P-rack algebra a restricted P-rack algebra if for all parameters there exists a parametric binary operation bullet such that a bullet is a bijection, one thing, and also it satisfies this condition. Again, for people that are familiar with solution in the non-parametric case, this is the structure group or the structure algebra for P-rack solutions, if there is this bullet operation. But here again, we have this strange parameter dependence. And you see here, you have a different orders. You have Ji, whereas in the right-hand side, you have Zij dependence. An example, I stick to the particular example of a triangle as defined it previously, like that. And now my bullet operation is defined like that. A circle Zi plus B circle Zj. Indeed, it turns out that these two operations satisfy this fundamental relation of the definition, namely the generalized parametric structure algebra in general, because in general, this bullet operation is not a group, apparently, in the general case. Okay, what we can do about this, we can, of course, identify now what it remains to be done. We would like, as usual, in the context of the quantum algebras, you need to identify some coproducts and so on, some co-associativity if possible. And that's what I'm going to do next. But before I do that, I would like to make a side note for the non-parametric case, for the parameter-free case. We introduced, again, with Bernard and Paula in our previous paper, in the case of affine quandles are special cases of racks, in the case where a triangle A is A. We found families of so-called affine quandles that generate the so-called pre-Lesch braces. So I introduced the notion of pre-Lesch braces, and the definition is the following. So I just give you this extra information to show you how much interesting structure there is and how many connections you can do by just studying these objects. So again, I have some X plus, this is a group, and a bullet operation. In general, this is a binary operation, not necessarily a group. And we say that the triplet X plus and bullet is a right pre-Lesch brace. If for all ABC, these two left and right distributivity conditions are satisfied, this 0 can be replaced. 0 is the neutral elements of X plus. And also the pre-Lie condition is satisfied. Okay, this is a well-known for people that are familiar with pre-Lie algebras. And if we say that this triplet is a left invertible, right pre-Lie skew brace, if there is a notion of invertibility, I'm not going to go further into details here. I'm just going to say that in order to define a Lie bracket out of this and some Jacobi identity to be satisfied, some extra conditions are required, and this takes a bit more of effort. But I will not dwell on that at this point, and I will come back to my parametric solution, and I will identify the first map that is a coproduct, and it turns out to be an algebra homomorphism. So if I start with a P-rack algebra and my universal R matrix, which is a solution of the Yang-Baxter equation, I defined this map, the parametric map, so family of coproducts, if you wish, from Q to Q tensor Q, such that delta prime, the parametric delta is defined like that. Notice here the change in the parameter. Here I have Q zik, zij, Qi zik, and this is the coproduct of H, okay? Such that here you have BC, such that B triangle C is A. So it turns out that this delta prime is a Q algebra homomorphism for all parameters Zij, and also it satisfies this kind of intertwining relations with the parametric R matrix. Notice that this relation satisfied only for Q, not for H. So it's almost like the coproduct we would like in a Hopf-like structure or by algebra structure, but not quite yet. But nevertheless, this is an algebra homomorphism, and for Q, we have a nice intertwined relation with the R matrix. Good. We can say a bit more about that. We can identify the N coproduct. So this is the N coproduct for Q, and this is the N coproduct for H. It has a particular form. You see clearly here that you have no associativity because a triangle is not associative in general. And you can show that for Q, the N coproduct of Q satisfies some kind of parametric co-associativity in precisely the sense I describe in this relation here. The parameters are very interesting. So I have parameters 1, 2 up to n here for QA in. And here I have 2 up to n minus 1, n minus 1, n. And here I have some other distribution of parameters, 2, 3 up to n, 1, n. And for the second, for the N coproduct for H, I simply have this condition. I don't have any kind of co-associativity. And again, delta n is an algebra homomorphism. So if I would like to make a statement now, a further statement, to include the notion of co-associativity for H as well, I have to introduce the bullet action of my restricted P-rack algebra. And this is precisely the reason that one is obliged in a sense to restrict a bit the algebra to introduce a notion of associativity and co-associativity. So now I'm in the realm of the restricted P algebra. Again, I have the same R matrix, the universal R matrix, but now my bullet operation satisfy this extra condition, have this extra condition between triangle and bullet, this kind of relation here. Again, is a parametric relation, which is, as usual, as in all our discussion here, it's quite involved, but nevertheless, it works out fine. Delta J, Z, Z, JK, the family of, a parametric family of coproducts is as before, but now the coproduct for A changes, and delta's HA is defined in this form such that B bullet C is A. And it turns out that in this case, that delta is again an algebra homomorphism, but now we extend a bit more. It turns out that all the elements of the restricted P-rack algebra intertwine with the R-matrix. The coproduct of the elements of the algebra intertwine, which is good because this is something that very much reminds us of the notion of quasi-triangular bialgebra. Parametric, nevertheless, but... And now you can extend, as before, the notion of a parametric co-associativity. The delta n coproduct is as before. And you have some extra conditions. You have the condition that you had before, but you also require that the bullet satisfies a kind of a parametric associativity in that sense, as I described here. So these conditions are sufficient to show the co-associativity of the coproduct. So this is the n coproduct, the parametric n coproduct for Q and its inverse, and this is the n coproduct for H. So you have HA1, HA2 cross blah, 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 provided subject to this condition. So this pi should be constant, and I define this capital pi like this. If I have two elements, P Z1 to A1 is just A bullet A1, 2, whereas the n product is defined like that. I use the parametric associativity to define it. Okay, which is precisely this one. This comes from this here comes from the fact that this condition is satisfied. And in this case, in general, for all elements of the restricted P-rack algebra, the parametric co-associativity holds, which is this one, is a parametric version of the associativity. And also the n coproduct is an algebra homomorphism, which follows as a natural generalization of the statement for the two coproduct. And the examples will be the same as we did before. And what is interesting for this particular example of bullet triangle that satisfy all the correct relations, it turns out that the product has this very simple form, is A1, Z1, A2, Z2 plus blah, blah, blah. In the parameter-free case, all this discussion we did, discussed in a previous paper, again with Bernard and Paula. And if X bullet without parameters anymore is a group, then we recover indeed a quasi-triangular Hopf algebra, right? We were able to identify the co-unit and the antipode. And it's what one would expect from studying solutions of the Yang-Baxter equation. Here, the identification of the coproduct and antipode becomes a bit more complicated due to the fact that we have all these extra parameters. So now in our setting, the parameters are part of the family as they define are associated with families of generators parameterized by them. Just a bit of a graphical representation. So this is the coproduct. Delta Z1, you have Z1, 2, the parametric dependence in the node, and you have in the foot 1, you have space 1 of the one factor of the coproduct and the second factor. You can generalize for the 3 coproduct, and this is precisely the co-associativity. So this is a delta, the third coproduct. This is Z2, 3. And you act upon Z1, 2. So you have the correct correspondence between dependence and the lines that corresponds to the different factors of the tensorial product. So Z1, 1, 2 is Z2, this is Z2, this is 2, this is 3, and in this way. So in terms of binary trees, you can in fact, using this recursion relation, which is the n co-associativity, expressed graphically like that. if you unfold the n-1, you end up to the 2-1 binary trees that corresponds to the different ways of expressing the n coproduct, all equivalent, of course. So an example is the fourth case, where you have 4 equivalent diagrams to depict the 4 parametric coproduct. So you have 1, 2, 3, 4 elements, and you have the correct parametrization. And you have 4 distinct cases. 1, 2, and 3, 4, depending on the action in the different components of your tensor product. So basically, this is the algebraic setting, but this has to do only with the setting on Pirac solutions, which is the algebraic description, the universal algebra, the Pirac algebra, and the corresponding universal R-matrix. But you remember we found solutions of a more general form, and there is an algebra for that. Basically, is an enhanced algebra, which we call decorated Pirac algebra, is the algebra we had before, plus some a family of extra generators we call W-A-Z-I-J. And all these relations, you have a new set of relations, the ones you had before, plus all the relations between W's and Q's and W's and H. This is a new algebra, and this algebra is associated with the general set-theoretic solutions. Very quickly, I'm not going to go through into details. Due to associativity, as we did before in the Pirac algebra, you can show that these 2 solutions hold. But if you look carefully, these 2 solutions are nothing but the conditions of an admissible twist we discussed in the first part of the talk. It's precisely the same conditions, which is somehow magic, but again, is the consistency. You have precisely the same coproduct structure that we had before. So the coproduct for W has the similar structure as the coproduct for Q. All the statements we did before hold. And of course, as we did in the case of the concrete set-theoretic solutions, all you need to do is an admissible twist to twist your Pirac solution to the universal set-theoretic R-matrix. I'm not going now to show how one shows the admissibility of this twist. It's a lengthy process, but definitely you can do that. You have a concrete expression for the twist, which turns out to be admissible. It depends only on H and W. And if you twist your universal Pirac matrix, you're going to find a twisted matrix. And if you go ahead and consider the fundamental representation, the n-dimensional representation, all you find is an n square by n square matrix of this form, which is nothing but the linearized version of the set-theoretic solution. So it all fits nicely in a consistent way from the set-theoretic frame to the tensorial frame. And I think I will stop somewhere here. Thank you very much for your attention.
Many thanks, Anastasia. Are there any questions? Remarks? Maybe not, or maybe in the chat. What are the chances for finding all solutions for the quantum Yang-Baxter equation?
Well, I'm not sure what you mean, find all solutions.
There is in the chat, finding all solutions for the quantum Yang-Baxter equation. What are the chances for finding all?
I'm not sure what you mean by finding all solutions. You have in this setting, starting from the universal algebra, this is very precisely frame, right? Very precise frame. if you mean what are the chances to finding representations of this algebra, then this is a business, right? One has to work to see what, except the fundamental representation, what other representations one can find. But then there is also the problem of classification of these new objects, the P-racks. So everything is open in that sense. So yes. The chances, I don't know, it's work in progress, let's say.
Okay. Are there any other questions? It seems not. So let's thanks again, Anastasia.
Thank you.
Thank you.
Thank you very much. Bye-bye.
Bye.